I won't have any specific presentation today. This is more designed as a hands-on session, something relatively similar to what we are doing with our clients when we are showcasing, we're implementing solutions. So sometimes after you deliver the equipment to the certain institutions, you need to implement that solution to organize that everything works smoothly and that everything is fully functional. So I will share my screen to show you the image of just let me see which screen is that. It's probably this one. Yes. So this is the image of the evoked potential. So as you can see on the left-hand screen side, we have the EEG trace, the raw data EEG, which is filtered, as you can see with these conditions. And we have a lot of triggers. And on the right-hand side of the screen, we have the evoked potential. So evoked potential is essentially the brain response to any kind of the stimulus. So the stimulus can be obviously visual, auditory, Vibro-Tactile. It can be also the sense of smell, and it also can be a combination of some of those. So what is important and what really describes which are the three main parameters of the evoked potentials. As you can see on the screen, we have a visual evoked potential. It's very well known N170, which is response to the facial stimuli, or where we present the faces or some objects or any image. And it has this very particular form, whereas there is the peak negativity around 170 milliseconds, hence the name N170, because it's a negative. And it can vary from even earlier of it, 160 to maybe 210 milliseconds. That is what we have observed. It has this particular positivity going or preceding N170 and then coming back. So this is the online acquisition. This is not the complete analysis of the evoked potentials, but you can clearly see that we have 1, 2, 3 distinctive peaks. This is the one of the interest. So this is what is meant by morphology of the evoked potential. The second most important parameter is latency. So in this case, it's 188 milliseconds. If we are having just the flashing on the screen or flashing lamp, it's very likely that you would have just the positive peak of 120 milliseconds approximately, although it is called P100. And the third, and that is also very important parameter or description of the evoked potential, is reproducibility. So we are supposed to reproduce the very same response in a consecutive experiments at the same day with a few hours apart, or even 1 month, given that all conditions are the same. So we shall go today to the practical example. So we shall pass to the hands-on, and I will now switch the video to the camera. Let me see if we can visualize correctly our setup. So over here we have the main computer, which would have this G-recorder program, which is very handy for the evoked potentials. It's a WYSIWYG solution. What you see is what you get. very intuitive, which allows you to clearly see the raw data quality as well as the resulting evoked potential. Then you would have the monitor that would be, this is going strange, where we have actually our stimulus presented. So for instance, if I run a paradigm, let's say some visual one is the easiest to exemplify. So we have here, let's say visual P300. And if we pass it to the big screen and run it, then our subject, in this case, Evoked, would be able to see it. So in this very same paradigm, we have these two Vibro-Tactile elements. One would be the target, one will be the non-target. And then we have our amplifier, which in this case is the mobile g.tec device with a cap with gel electrodes. And I will ask now my other colleague, Frankie, to help us prepare Evgeny. In the meantime, I will stop the paradigm. Okay, so you see Frankie is actually positioned in the cap. Very important step is that the vertex, the CZ electrode will be over the vertex, which is the half of the distance between the anion and the nasion. And likewise also, he is looking for midline to be also in the middle of the distance between the ears, left and right one. Now, this is the pro-flexible model, which has these detachable caps, which is very handy for potential and other experiments, where you have a need to conduct several experiments during the day, so you just switch in between the caps. So Frankie is now putting the gel in the ground electrode, and the electrode that will be used for the measurement of the impedance, maybe that be the CZ as well. So ground didn't. Again, these are the active electrodes, so it always goes pretty quickly. And I will now switch off to another camera and start measuring the impedance. Okay. Okay. Now, very well, we shall now again share our screen. Here it is. And we will now pass to the acquisition mode. So now we will connect to our g.Nautilus, which should appear in this list. Here it is. Once it is connected, we need to select some parameters, the channels that we are going to register. In this case, we want all 32 channels with 500 Hertz. There are some other options as well, like digital trigger. Validation indicator is important when you're running the real-life experiment studies where the subject is mobile. And if you lose the connection with a amplifier, then you will have the 0 value here. Otherwise, the value is always 1. The range is depending of the ambient, but typically up to 10 meters. In the open space, it can be actually even longer, up to 12, 13 meters. We recently did one demo recording in Turkey and in Istanbul, and we managed 12 meters without any problems. But also sometimes it would work only for 4 or 5 meters. It depends a bit on the ambient. Now, once we have selected all our channels, we need to select the proper montage. In this case, 32 channel Nautilus. And now you can see that we have all of the channels named properly. Now we are ready to make the impedance measurement. And Frankie is probably finished preparing. Evgeny, if not finished, quite close to it. Okay, all right, so we can make actually this a bit more visible. So we are missing some 5 electrodes. Maybe we would need to improve a few afterwards. As you can see, with these active electrodes, there is no need for scrubbing and preparing the scalp. Impedance can be pretty high, and still the recording will be good, especially with the evoked potentials where you have the averaging of the trial, so signal to noise ratio is climbing up. Clearly comparing to the passive electrodes where you have to bring this impedance quite low. For certain evoked potentials, especially those of the low of the short latency, where you have a high sampling rates and which might be a bit in the deeper structures. I can remember that the ABR, for example. So it's a P of 4, Frankie, that's still black. In those, you might need to use passive electrodes all the same. And the impedance should be as low as possible. I usually bring to 1 kilo. Although, I mean, a lot of those scrubbing is slightly unpleasant. So you would use the abrasive agent to lower the impedance, which feels like rubbing the sand against your scalp. So usually each of the colleagues is once volunteer, and then they all start running away when I ask them to be the subject again. So PO4 is getting better. Also AF3, so it's anterior frontal electrode that is still high. Okay, it's getting better. What is very nice feature in G Recorder, thank you, Frankie, this is acceptable now. Very well done. Nice feature in G Recorder, once you press the stop button in the measurement of the impedance, these values, impedance values for each of electrodes will be automatically saved in the file. And I can show you that pretty quickly. So here in G Recorder, we have today's measurement, which should be here. Oh, sorry. It should be actually in the impedance measurement folder. And here it is. And over here, you can see this is the serial number of our device, no doubt about it. And then we have the values of the impedances measured. So that comes very handy for the everyday lab, so user doesn't have to worry about that. And if afterwards is some doubt about the values measured, then you can always go to the file and check out where your impedance is. So the next step would be actually to confirm the quality of the EEG. And for that, we need to use some filters. So let's say 0.5 to 30 Hertz. That's pretty typical. So these are the visualization filters only. Raw data are saved completely unfiltered, just as they come from the amplifier. That's also very important for the recording of evoked potentials, unless you're doing for BCI application. In BCI application, because it's the immediate application, then you don't need posterior analysis, then you can filter data on the amplifier itself. So you saw that Evgeny was closing his eyes, and when he closes eyes, he has a very nice alpha. Excellent. So now if you can blink a few times, please. So we are looking for these strong frontal artifacts that are typical to the blink. So not so strong, just a few blinks, please. Yes, this is what you want to see. You want to see disappearing this artifact as we go backwards. So at the OZ electrode, there is no. And if again he clenches his teeth, then we will see this typical EMG artifact. So even if you don't have available impedance measurement, which happens with the dry electrodes, that is simply because dry electrodes have too big impedance to be measured. You can evaluate the quality of the signal by looking at the EEG. Okay, very well. So the next thing will be to prepare the stimuli. And if we are looking at the organization of the evoked potential experiment, we obviously have the amplifier with the subject who is not shown on the image. Sorry, why is this running? And we have a stimuli. In our case, we will use our own software, Paradigm Presenter, which can be run from the same machine. We actually implemented solution for both G Recorder and MATLAB. I will go later into details. But if your existing lamp has some other packages, we are also compatible with them. So a lot of labs have, for instance, the presentation or the E prime. Then we have a small trigger box, which is looking like, I can show you in a minute, which is looking like this one. So you would put this parallel port trigger cable, one end to the amplifier and the other one to this USB to power port adapter, which is frequently used, and all of the users are familiar with that, and it works nicely with both of them, E prime and also the presentation, but also for some other packages. I'm not sure if we did it in the US with the Cedric. They're also popular there. It works nicely with the PsychoPi. So for the PsychoPi, we developed a specific code because the original PsychoPi input-output routine does have some minor bugs. It does work, but it gives the wrong values. So it will work with any packages. And then obviously, ideally for the ERPs, you can use the G Recorder. That is the circuit. And as you have seen also on our desk, we have that organized. Another thing that is important is not to show the acquisition computer to the acquisition screen to the subject. So again, it should be concentrated on the task that he has. So now going to the task, we should select the paradigm. So we shall start with sorry. with a paradigm for the Vibro-Tactile. And in this Vibro-Tactile, we can see how it is actually organized. So we are having a target and non-target. We have several different node targets for the visual part and just one target. We are using this stim box that you have seen a few moments ago, where there are like two Vibro-Tactile elements that were vibrating. The left one, which is the target, correct, Evgeny? Mm-hmm. So that's another thing that you have to pay attention. So when you're conducting study, you should give the clear instructions to the subject or the patient what he or she is supposed to do. And you can check up if they did understand it. You should make them comfortable to ask if they have any doubts about that. Now, since it is very difficult for me to show you vibration because he will be feeling, but we have no means how to transmit that over the internet. I'm using this visual stimuli. So now we have seen that the code for the target is number 2 and number 1 is for the non-target, and that is what we define in our markers. That is how we receive these UDP messages. There is certain delay actually with this technique. However, we did the measurements extensively and we compensate in software for those delays. And now we need actually to design the evoked potential window, so where we will be doing the pre-visualization of our hopefully final result. And the suitable filters should be 0.530, not in every single case, but in general you can see it very nicely. Because we are looking for the P300 evoked potential, so the positive peak around 300, 330 or 280 milliseconds. We want to have the larger window. So time base for our window is 700 milliseconds. You can also put it 600. Now we will add 2 events. The first one will be the target one, and it will have the blue lines, and the second one will be the non-target. And now we are essentially ready. When I press the OK button, there should be two windows popping up. So one of them is non-targets. We can actually redraw them. And the other one is targets. Here it is. As you see, these experiments always take some time to prepare, but it's fairly simple, especially this one. So this is almost from the school book. And then you can also rearrange a bit the live window for the raw data to 5 seconds, let's say. And now we also want to go to the presentation window. So hopefully you're seeing now my presentation window, the window that is in front of Evgeny, our subject for today. So we will be using this paradigm, and we will just make an initial run to see if it works. So you see this is pretty long sequence. You don't have to run it all the time. And whenever there is this colorful image, the one with the beach, then there is the vibration in the left, on the left pulse of Evgeny. So very good, everything seems to be working. Now we will come back to our window, our acquisition window. And we will again play the EEG. So because this is the DC amplifier, it always takes a few seconds to stabilize the baseline. And also another thing, because we want to run just okay, just the Vibro-Tactile stimulation. I shall take off the screen from Evgeny. So his task will be to count how many numbers there is the vibration in the left pulse. I will switch the cameras again. So we have a couple of, so we want to place over here on the pulse, the Vibro-Tactile element. We have a couple of bracelets. Yes, thank you. So again, it will be collaborative and prepare himself, so I could film it for you. And then the other one, we just need it there. Okay, very well. Hold on. Okay. This is not as elegant, but when we are doing it with one hand, you should be able to do it nicer. And we are looking for the relaxed position. So as you see, Evgeny has accustomed to have his legs slightly contracted. So we are checking that no muscles are contracted. You should instruct subject not to laugh, not to talk, not to cough. Blinks are inevitable, so that's pretty fine. And now we can actually start the acquisition. I won't be recording, I will just be showing you how it is. We confirm again with our subject that he is ready. Yes? Yes. Okay, very well. Starting in 10. And then over here at the target, so whenever we see this beach image, there is another trial added to the average of the resulting evoked potential. So if you have, for instance, one of the noisy averages, noisy trials, you can restart it over here, and it will be fine afterwards. You can in the offline analysis eliminate just the noisy trials, not all of this. But this allows you actually to start from the scratch and have the clearer image. Yeah, you see it's pretty rough. So maybe over here we have something that looks like P300. So you would usually need a lot of trials. Yeah, it's building up slightly. Perhaps. So yes, we can zoom in at a certain period. Also, another thing that we would be using when we are doing Vibro-Tactile element is probably the grounding. So this is the grounding bracelet that we didn't attach at the moment. Okay. And then we should hopefully end up with a nice P300. However, I'm already running a bit late. I'm sorry, so I will just stop the study. stop the paradigm, and let's try to do the other modalities. And we have also another programs. Thank you, Evgeny. Okay, switching back the camera. Take off this. I shall quickly take off the bright lights invasive. So we have another two modalities. Another program that we have is actually Simulink. g.tec is for the Simulink, which you have seen these days before already. And I will show you actually how you can build the model quite quickly. So I shall try in 10-15 minutes to build the model. It's pretty simple. We have a lot of blocks custom made. The first one is related to the amplifier, which is our G.Nautilus. And if I double click it, I should be able to connect to the Nautilus. Here it is. I can select all 32 channels. I can use, for some reason, it's not working. Okay. Switch it back off. And quickly restart it. On. And try it again. It takes a few moments. Now we have all of 32 channels selected, 500 Hertz. We're quite happy. We won't be using any filters. Then we will add the paradigm presenter block, and we might be doing the visual one. So let's say that we do the N170 test. And this would actually amazingly work, although it wouldn't give, sorry, any results. So if I start the model now, I have the paradigm already running. And we can close it. So how would we complete the model? We would need first to filter the data. So we add the bandpass filter. And we add the notch filter. And then we actually have to put the sampling rate, which we can read with this command directly from the amplifier. And not to write it all at the same time, as programmers already know, everything is copy-paste. Now we want to save that, so we are saving data. To save the data, we have to add actually the trigger information, which is coming from the group, if you remember, of the paradigm. It's coming from the group. And we are having the EEG data. And we can also show the raw data, again with a trigger. So, just like that. Another block that is very important, and that is quite a handy one is the raw data block, that we can show the raw data running with the filtered data. Okay, so another thing that we have to think is of the time and also the sample time. So the sample time is actually 1 by 500. And this should do the trick. Yes. And now when we play the model, we are supposed to see the raw data. And if we open it, here we have a nice EEG from Evgeny again. Can you please blink? Yeah, you see the blinking, excellent. And we saw the alpha over here. If you look at the home screen, then we use it at the 10 Hertz. Sorry, 10 seconds. So now again, he has the eyes closed. It looks very nice. Over here, he opened the eyes. You see how the eyes artifacts are disappearing on the posterior channel. So that's very nice. Thank you. Now we stop it, and because we are doing the evoked potentials, we need to actually generate the epochs. For the epochs, we need the triggers. So we have this trigger element. Where we were going to use this external trigger from the group ID. However, I won't connect it just yet. You will see why, because we have two conditions, if you remember. So we can use the compare to constant block, and one of the condition is 1, the other one is 2. So over here, we will say yes for 1, which is our target, and apply. However, it has to be in the specific format, and that will be our external trigger, which is coming from the group ID. Now we can also we need also to add the data. Data can be filtered actually. That will be perfectly acceptable. Then we need to design the window time base, which is in our case again 700 milliseconds. We have pre-trigger period, which is used for the baseline correction. And then we also can exclude the trigger. Then we add the averaging block. And for the evoked potentials, we will be using vector scope. So we can correct the baseline. Okay. And then we do the vector scope over here. Nice. Now in the vector scope, we won't have the number of the trials, so we can simply add a counter, and we get increment information from the trigger block. Then we can also use display to show the number of trials. And you can arrange it like this. You can put it a bit bigger so we could see the number of trials. So it takes some time, but as you can see, this is not very complicated, and it's quite effective. So if I again select the presentation window, okay, and start the model. Okay, so we didn't include the validation. It's a very nice intuitive visual tool. It's not very difficult to sort it out. So we need a correction time to 0.1. Okay. Yes. Oh. So once you manage to have it, so let's see why that doesn't connect that quickly. Yes, here it is. It's trying to communicate with g.tools. It is starting. The stimulation, and these are the already trials. So since I'm actually running a bit late, I will show you how that looks like with a video. So we have a nice video here. We have, this is in the G recorder done with a high amp. We have 64 channels, and this is the paradigm showing object and faces. Then we have the raw data and resulting evoked potentials. And as you can see, we have a very nice M170. Yes. Good, and now we are going to the final one. So we're going back to the G recorder. Quickly open it. We will be using a different paradigm. Which is this simple G recorder, which is designed to get us the N100 auditory response. So if I start the paradigm, it should be beeping. So we have, so when there is a target, there is a beep. And as you can see here, for this beep, we have another trial. You can stay with the eyes open here, please. Thank you. And then over the time, we should get actually the N100. So maybe maybe now another example from the, just to see one P300 and to show you some additional features that we have available in the Simulink. So this is from the Visual P300 from the model that you have already seen. So maybe I show you the paradigm again. Here it is. You can disconnect those. So again, the same thing when we have if I share in the simulation screen, you can see that we have this visual paradigm. Again, the same thing, we are looking for the beat, for the colorful image. And okay, and now again, coming back to the first screen. We will have the template opened from our database. And in examples you can find, so this is actually supplied with our system. We have this model which we can run. And then we can visualize the standard raw data. Obviously, because of the DC offset, it takes some time, but we can actually go to plus minus 50 microvolts, and here we have the resulting EEG. These two channels are actually the trigger channels. We can minimize that, and what is also interesting is the EP scope. And here we have our data, so we have the possibility to show both non-target and target on the same screen. We can even actually show the significant statistical difference between two of the events of two markets. And with this bubble scope, which is already available since the previous version of the g.tec, we can have the activation even in 3D in 3D space. So here it is. And as we can see, usually parietal area has the best responses. So these are these channels here. And yes, with that, essentially, I would conclude my presentation, and I would be available now for possible questions from the audience.
Thank you very much, Sloppy. Olaya is saying it's amazing how you can make a whole experimental pipeline in a visual way. And you have seen it just takes a few minutes to set it up. Somebody is asking, do you have a very consistent way of setting up or putting on the EEG cap and all the electrodes?
Well, that's pretty technical task, so it comes with the practice. Practice makes perfect. Using these active electrodes helps a lot. So the whole setup took 5 minutes to prepare. I don't know if that is the reply to the question, but that's all to the consistency. There is not too much to worry. You have to position the cap over the CZ. You have to align the midline with the nose line, assuming that the subject has the straight nose. Joking aside, because all other electrodes are fixed on the cap, once you have these two electrodes positioned correctly, there is nothing to worry about.
But you also have to remember that for the g.tec systems, the electrodes are inside the cap and they stay inside the cap. So all what you have to do is you put on the cap, you align it, you fill it. Except if you use dry electrodes, then you don't even have to fill it and you can start recording. There are many other systems where the electrodes are detached from the cap after usage for cleaning. This is not necessary here for the g.tec system, so you can clean together with the cap and the electrodes stay permanently inside the cap. And this has a lot of advantages. First of all, you are much faster. You don't have to search for channel number 1, 2, 3, 4 because they're always at the same position. And of course, you're also not making mistakes by exchanging, for example, 16 and 17. Then your results will also be problematic. And another important advantage is that electrodes don't break down so quickly because you don't have to remove them and you don't have to insert them. And this altogether saves a lot of time. This is very important for doing experiments because when you can assemble quick, your client, your patient, your student is still fresh and you get much better results. Next question is, what mechanisms does your system have to detect when corrections are needed?
So there is actually possibility in the G recorder. Let me see if in G recorder you can set up actually amplitude level above which the trial is considered as an artifact, and you can select specific electrodes. So usually sometimes select the frontal, but you can essentially choose any number or all of them, all of the electrodes to be monitored for the certain threshold. So threshold is usually set up high. That's the one thing. Another thing that you usually have the help is the period just before the stimulus. So this 100 milliseconds would be very helpful if you have, for instance, fluctuation of the baseline to stabilize that. And as you could have seen, both in the G recorder and also in the HiC solution, we have the possibility to automatically correct the baseline. So those are two major ones. For certain experiments, we would allow to have certain articles into blinks or so, and then you would essentially take them out during the analysis. You can use, for instance, independent component analysis, which is the most popular method for that.
And you can also hear that Santi is awake. She's waiting for another experiment. The next question is, how do you optimize stimulation parameters to ensure reliable EPs and also to avoid fatigue or adaptation of the person you're measuring?
Yes, this is interesting question. So these are the schoolbook experiments, and it's they are pretty well studied, so you know what you would have to do. I think it's the most challenging when you're doing some different tests. So, for instance, we are doing lately some experiments with the flight simulators, and we are looking for the P300. For instance, every time that subject, that the pilot looks at the instruments, we want to see what is the P300 level in those moments. So over there is a bit more difficult to select them, and you usually go sometimes by the common sense, which is not the best explanation for the scientific experiment, but it also counts. Then you go by the previous knowledge of P300, what is important, how to evoke it better. Usually, if you're running BCI experiments, then you should be sure that you provide the adequate feedback to the subject, because subject, when it has feedback, it has much higher accuracy than without the feedback. So I said it's more challenging when you're doing some specific study rather than the BCI. Also, another thing that you can do, you can optimize actually the conditions. So for P300, you know that, for instance, high levels of the coffee intake could affect results. And yeah, so there are a lot of tiny details that one has to take into account.
So how do you actually optimize how many trials or stimuli you need for the perfect DP? Because for auditory evoked potentials, if everything is correctly done, you don't need many trials to get a huge auditory evoked potential. And then if you let it run longer, acquiring more trials like it's traditionally done, then you can see that the auditory evoked potential gets even smaller. So how do you optimize?
Yeah, so I'm not really the scientist, so I wouldn't be able to tell you exactly, but I'm just following from the literature. What are the recommendations? So for the P300, usually you could get a nice answer after 40 trials. Some other evoked potentials like the ABR takes at least 500 of them.
But for the EBRs, you can click much faster, so the acquisition doesn't take so long.
Yeah, absolutely.
When you're doing auditory stimulation, what are you actually using, and when? Clicks, tones, speech, chirps?
So we are using the beeps usually for our showcasing. I'm not that good with auditory experiments. Chirps, clicks, etc. It's used in the clinical practice, and there is a very well documented. There are even reference values by the age group and the type of the stimulation, what latency the normal population would have, and so on and so forth.
It's depending, of course, on the application, what you should do. Daniel, for example, for the ABRs, was saying he's using chirps because with the chirp signal, he can activate the whole ear channel at the same time, exactly the same time, because the different wavelengths travels a certain time to the inner ear and to the outer ear. And with a smartly chosen chirp signal, you can just get the maximum stimulus. This is very nice for ABRs where you want to have the maximum. For testing unresponsive wakefulness patients, we use, for example, high and low tones because they are very easy to understand for patients. So it's just high and low, very easy to explain. And they have a very good timing because it's a very steep pulse. So we can trigger precisely and we know exactly when the person starts to hear it. For other experiments like N400, where people should detect words in congruent or incongruent sentences, like Sloppy is an EEG expert or Sloppy is an I don't know, fisherman, then you would get the fisherman N400 potential, because it's nonsense, more or less. Then people have to understand, of course, the language, the words, and then a big problem is the timing, because you don't know exactly when the brain starts to figure out what it's hearing. So you need the auditory cortex, first of all, to hear the words. Then you need Wernicke's area to understand what the person is saying. Then, of course, you have to understand the word in the proper language. Then you have to do some cognitive processing to figure out if this sentence is correct or not. So the timing gets diminished. And this is also a reason why you need many repetitions to get these evoked potentials. So it's very much dependent on what you want to do. But for all of them, a very precise triggering is essential. We can very nicely see it with auditory evoked potentials. So we have, for example, this audio trigger box where we feed back hardware triggers. And if we use hardware triggers, then we just need a few clicks. That's actually the wrong one, Slappy. Then we just need a few clicks to get the perfect auditory evoked potential. So we are talking of 5, 6, 7, almost nothing. And if we don't do that, then you need a couple of hundred to develop a nice IEP. And with perfect timing, the IP is just much bigger. This is, of course, also super important for scientific publications.
Yeah, so this is the audio box. I put the Steam box moments ago before I saw in the chat somebody was asking about the Steam box. So Steam box has 8 inputs and outputs on the frontal panels, but you have more. You have a 16 in this sub-D connector. It is also available as a block in the Simulink, so you can control it completely, and it also has the C and the MATLAB API for it.
Next one is, how do you deal with problems like hearing loss or background noise, like Santi barking during the experiment?
So in the case of the Santi, you would definitely manually take off that trial, because it's very difficult to control that. I usually do sometimes record double triggers, so using the software and the hardware triggers, and also I'm recording the sound channel. If you record the sound channel, you probably notice that, for instance, on mobile phone, you have that voice recording which has the typical speech waves. So the stimuli and the ambient noise would be pretty much the same, and that's how you could actually figure out which one is which. About the hearing loss, I don't know. I was working before in the clinical field, and they have a very specific protocols for that, but I'm not knowledgeable enough to say about that.
Again, depending on what you want to do, maybe you want to investigate hearing loss. This is what Daniel Strauss and Farrer are doing. They are using the EBRs to describe the amount of hearing loss. So that's the scientific question per se. If you are running a P300 experiment and somebody has maybe left side hearing loss, doesn't matter, because you get all the information into the brain via the other ear. So it's irrelevant. Then there might be some left and right studies where you investigate stereo auditory stimulation. And then it's, of course, becoming problematic. And then maybe you need on one ear more intensity than on the other ear. So you can take care of that. And when you're running a Vibro-Tactile stimulation experiment where you just want to see Vibro-Tactile EPs, and you don't want to have any auditory contribution. So you can also hear these tactors when they are switched on. And this is also producing an auditory component. So if you want to blank it out, you can just use headphones where you feed in brown or white noise. So mostly people are using brown noise. And then you are just not hearing the clicks, and it's purely somatosensory. So there are different ways to work around that. And with that, we are finishing another practical session. Slobby and Yevgeny, thank you very much for the nice demo.